Whenever shafts turn, wheels rotate, and parts move, bearings are needed to reduce the wear and heat caused by friction as components rub together. In this program, we will look at the different kinds of bearings. We'll see how they work, and we'll look at the problems that may occur when they are not properly installed and maintained. Let's start by looking at what bearings do. Besides reducing friction, bearings also do two other important jobs. First, they bear or support a load, typically the components of a machine or the forces developed during a machine's operation. Second, they guide and position moving parts accurately to ensure true alignment and smooth running without wobble, shake, or slackness. This requires a close fit between part and bearing. These three functions are interrelated. The tighter a shaft is held in a bearing, the more accurately it will guide and position, but this will lead to more friction. A small bearing will generally produce low friction, but will not carry heavy loads, so each bearing application is a compromise. One point worth remembering is that all bearings will eventually fail because the materials will fatigue. But that's part of their purpose. When bearings fail, they keep other more expensive components, like shafts, from wearing out. In fact, bearings are rated in part on how long they will last before failing. They have an expected working life, and if they are correctly installed and suitably lubricated, they will usually last for their working life. The term life can be defined as the number of revolutions or the number of hours at a given speed that a bearing will operate before fatigue or failure occurs. This is calculated by manufacturers based on the number of revolutions that 90% of a group of similar bearings will reach or exceed before they fail. Bearings wear out much faster under heavy loads. For instance, doubling the load may reduce the life of a bearing to 1/10 of what would be expected normally. So bearing life can be extended by either installing a larger size or by reducing the load. But what is load? Loads can be thought of as coming under these three headings: radial loads, thrust loads, and combination loads. Most bearings are designed to carry radial loads. These loads produce forces acting at right angles to the shaft. An example of this is the pull of a V-belt on its pulley bearing. Many bearings are designed to take thrust or axial loads. These loads produce forces acting in line with the shaft. A propeller or a drill, for example, puts a thrust load on its bearings. Some bearings are designed to take combination loads, in which both radial and thrust loading is encountered. Such a bearing would be needed in a car wheel. There are two main groups of bearings: plain bearings and rolling element bearings. They do similar jobs, but they are designed differently. First, plain bearings. These can be thought of as just one part of a three-part assembly: the bearing itself, the lubricant, and the moving part. Plain bearings are manufactured in many different sizes, shapes, and materials. The most common are sleeve bearings and half-shell or split bearings. They all function essentially as a collar that encloses and supports the moving part. The sleeve is usually stationary and is called the bearing. The moving part is generally called the journal. Sleeve bearings have been made from a whole range of materials, from various types of metal to plastic. The sleeves must be able to hold on to an oil film well. They must be elastic enough to give under temporary pressure. They must be soft enough to accommodate dirt and other matter in the oil. And finally, they must have adequate mechanical and fatigue strength. One of the most common materials for plain bearings is cast high-grade leaded bronze, or bearing bronze, as it is sometimes called. This material has excellent load capacity and anti-friction qualities. Another cast-bearing material is aluminum bronze. It's used for heavy loading and where shock loading might be a problem. Finally, sintered bronzes and metals. These porous materials are produced by a special process that compresses and heat treats powdered metals in a gas atmosphere. In plain bearings, friction is minimized in two different ways. Often friction is reduced by maintaining a lubricating film of oil or grease between the bearing and the journal. The oil film adheres firmly to each of the two moving parts and prevents metal-to-metal contact. This adhesion is more than mere wetting. It is a chemical attachment between one end of long thread-like molecules in the oil and the surface layer of the parts. Sometimes the lubrication is built into the bearing material. Porous bronze bearings, for example, are about 20% lubricant by volume. They are used extensively in office, textile machinery, and the food industry, where grease or oil lubrication would be inappropriate. In bearing operations, a good lubricating oil must be able to retain its lubricating properties while allowing two rubbing surfaces to slide smoothly over each other and produce only small amounts of heat. This can be achieved in two ways. One way is molecular film lubrication, also known as boundary lubrication, sometimes called hydrodynamic lubrication. In this method, only an extremely thin layer of lubricant is needed because it adheres to both surfaces and is not removed by pressure between the parts. The second way is known as full film lubrication. The moving parts are separated by a relatively thick, continuous pad of lubricant. Often, internal grooves or channels are cut on the inside of the bearing to direct the lubricant to areas of high pressure. In some applications, external pumps are used to maintain the oil pad between the sleeve and the journal. This is sometimes called hydrostatic lubrication. With full film or hydrostatic lubrication, the viscosity of the oil, its thickness or resistance to flow, is an important factor. A good pad of oil needs to be maintained under pressure and at working temperature. In some applications, such as the internal combustion engine, the lubricant has another important function, cooling the moving parts. Most of the heat generated in the bearing surfaces must be carried away by the oil. Much of the efficiency of plain bearings depends on the ability of the oil to maintain a constant lubricating film between the moving parts. If there is no metal-to-metal contact, these bearings have a relatively long life. Plain bearings are mainly used in relatively low-speed, high radial load applications. Since the sleeve and journal have a large contact area, plain bearings have a greater capacity for shock loading. They are used widely in construction and mining machinery. Now, rolling element bearings can carry radial loads, thrust or axial loads, or a combination of both, often in high-speed applications. Inside the bearing, the rolling elements are arranged in one or two rows of evenly spaced steel balls or rollers. They move freely between inner and outer rings. Grooves, or races, are cut into the inner surface of the rings to guide the rolling elements. Often, a cage, a retainer, or a separator keeps the rolling elements in position, aligned correctly, and separated, so they do not touch each other. This also keeps the same number of rolling elements supporting the load at any one time. Seals and side plates of various materials are used to protect the rolling elements, to keep the lubricant in, and to keep contaminants out. Rolling element bearings can be divided into 5 main categories. Ball bearings. These can be used in either a single or double row, and are designed for both radial and axial loads. This type is usually used when the shaft can be maintained in good alignment, for example in spindles or turntables. Cylindrical roller bearings. These are used extensively to carry heavy radial loads, and when loads are subject to sudden variations and shock conditions. They are particularly useful where loads run out of balance or where the direction of load is continuously changing, for instance in paper or steel mills. Spherical or convex roller bearings. These are most often constructed with 2 rows of rollers and are designed to carry both radial and axial loads in either direction. The inherent self-alignment of spherical rollers makes them ideal for heavy-duty applications. For example, in ship's propellers and railway axle boxes. Tapered roller bearings. A unique advantage of this type of bearing is its capability to handle heavy radial and axial loads independently, as well as simultaneously. For example, in car wheels. Finally, needle roller bearings. These may be used with or without an inner ring, directly on a hardened shaft. They usually carry heavy radial loads and require only a minimum amount of space. Lubrication is essential in any bearing, not only to ensure smooth operation of the bearing, but also to act as a protection against contamination and dirt. Half of all premature bearing failures are caused by poor lubrication. Grease lubrication is usually used where low to moderate speeds are needed. To avoid overfilling, which can lead to churning and overheating, manufacturers usually pre-fill bearings with the correct amount of grease, enclosing them with non-reusable seals. Oil lubrication is used for high-speed or high-temperature applications. Often the oil is circulated around the bearing to remove heat. On horizontally mounted bearings, the oil level should reach the lowest ball or roller in the bearing. Avoid flooding the bearing because the rolling elements will churn oil and raise the temperature. It is essential to protect bearings against dirt and moisture, and wherever possible, they should be completely enclosed. Many bearings are supplied in housings that help provide accurate shaft alignment and support for radial, thrust, and combination loads. Three common types are the pillow or plumber block, the split pillow or split plumber block, and the flanged housing. Most bearings in these housings are alignable or self-aligning. The bearing is able to swivel within the housing to line up with the shaft. Usually the bearing can align itself only a few degrees. Whenever possible, housings should be installed at right angles to the shaft. Under the right circumstances, bearing life can be long and trouble-free, but under the wrong conditions, frustratingly short. Let's look at the wrong conditions so that they can be avoided. Excessive loads on a plain bearing will squeeze out the lubricating film that normally separates the bearing from the shaft. Metal-to-metal contact increases friction and heat, which thins the oil or grease even more and contributes to further deterioration. The bearing metal wears away quickly, sometimes even melts. In a rolling element bearing, failure usually results from metal fatigue rather than frictional wear. The steel may become brittle and break up. Metal fatigue occurs in a rolling element bearing because the load is concentrated in a very small area. Typically, only 3 or 4 rolling elements at a time support the entire load, and the points of contact between the rolling elements and the races are very small. This means pressures are very high. This concentrated load actually dents the races and the rolling elements. Normally, the steel springs back each time a rolling element passes under the load, but eventually, the steel work hardens. Instead of springing back, the steel breaks up and is permanently damaged. Fatigue failure and permanent damage eventually occurs in all loaded roller element bearings, but heavy loads accelerate the process. As we have seen, doubling the load can reduce bearing life by a factor of 10. It's a point worth emphasizing that bearings should not be subjected to loads they were not intended to bear. If the load is too heavy, the bearing will fail quickly. Shock or impact loads, rough treatment by an operator, and dull or chattering tools will also shorten bearing life. Bearing designers may expect rough service, but no bearing will take abuse indefinitely. Vibration has an adverse effect on bearings. Machinery will vibrate if any part of it is out of balance, bent, or loose. If bearings are to last, the parts must operate smoothly, without shaking or rattling. Improper adjustment of equipment can overload bearings. This belt needs to be under tension in order to transfer its power without slipping. Tension adjustment should not exceed the manufacturer's specification because increased tension on the belt will lead to an increased radial load on the bearing. Additionally, improper adjustment of bearings may cause overloading. If this nut is over-tightened, the inner rings of both bearings will be pulled towards each other. Both bearings will be axially preloaded. That is, they will be loaded even without an external load being placed on them. Quick failure will result unless the nut is carefully adjusted to the manufacturer's specifications. Long shafts may also cause bearings to become overloaded. As a long shaft warms up, it lengthens. If the shaft expands enough to take up the end tolerances built into the bearings, then a thrust load will be produced, affecting both bearings. Any kind of misalignment between two coupled shafts or between shaft and bearing will also impose an unnecessary load on bearings. In a misaligned plain bearing, two areas are heavily loaded. When a rolling element bearing is misaligned, the result will be an uneven thrust load on the rings. The result in both cases will be increased friction and heat and early failure. When failure does occur, two signs of wear may indicate the reason for the failure. The most common is spalling. Spalling occurs when the metal in the bearing becomes fatigued and the small bits flake off the rolling elements and races. Brinelling may also occur. This is caused by the rolling elements permanently denting the races. It happens if the bearing is overloaded, and it happens if shock loads are applied when the bearing is stationary. With both these types of wear, the bearing will have to be replaced. Spalling cannot be avoided, since all bearing metal eventually becomes fatigued. Brinelling can be avoided with care. When bearings fail early, it is sometimes because they were not selected properly. A bearing may fail early if it is not correct for the application. Some inexpensive semi-ground commercial bearings may appear similar to more expensive high-precision types, but they will not last as long. Some sealed bearings may be interchangeable in terms of proper fit, but the interior may be completely different and unsuited for a particular application. When replacing a bearing, always try to replace it with another that bears exactly the same reference number. If you must use a different bearing, check a bearing guide for a direct equivalent or for an alternative suited for the application. In this program, we've looked at many of the common bearings used in industry. We've seen how they work, and we've seen some of the common problems that can occur before and during operation. When correctly installed and maintained, bearings enable machinery to run reliably and efficiently.